Hello children, we are on lecture 2 related to the Bohr model. Before this lecture we have done the Planck's quantum theory, in which we came to know that the radiant energy, and we consider the ray, is made up of large number of bundles of energy, and each bundle is known as quanta, and that bundle in case of light is known as the photon. So the Bohr model was developed after there were few drawbacks in the Rutherford model, and the main concept about the Rutherford model, the drawbacks of them are an atom that revolving electron will lose energy continuously, and when the electron is losing the energy continuously, then it must be following a spiral path, and ultimately it should fall down into the nucleus. And if it falls down into the nucleus, the atom must collapse. But it doesn't happen. So what was the reason behind it was not explained by Rutherford. Even the previous concept, that is the hydrogen spectrum, line spectrum, that was not explained by Rutherford. So to overcome these limitations of Rutherford, the Bohr model came into light, and it was given by Niels Bohr in 1913, which is based on the Planck's quantum theory of radiation. So now let us talk about some of the important postulates of the Bohr model of atom. So the first one, which was coming from the previous models also, that an atom consists of a small, heavy, positively charged nucleus in the center, which is surrounded by electrons. The electrons in an atom are revolving in a fixed path, and these fixed paths are known as orbit. And these paths are having definite energy. Each of the paths is having the definite energy, and these paths are now known as energy shells or energy levels. So if we used to represent the simple structure of the atom, they are represented as the center part is the nucleus, and the first shell is represented as K shell. We used to call it as 1, and then the second shell is known as L shell, and the numeric used for it is 2. So a simple representation for it is the center part is nucleus, and the nucleus comprises of proton plus neutrons, and these are the orbits. These are the orbits or the energy levels or the energy shells in which the electrons are revolving. So this was the beginning part, the first step, that atom consists of a small positively charged heavy nucleus at the center, and the electrons are rotating in these circular orbits, and they are revolving also. So now we come to the second point of the Bohr's model, the second postulate regarding it. These are, the second point says the energy of the electron in the orbit does not change. That is why the electron is not getting the spiral nature and is not falling at the center. That is, the atom is not going to collapse. So this point explains that the energy of electron in the orbit does not change with time. That is, as long as the electron remains in a particular orbit, it does not lose or gain energy. That is why a new term used for it is the stationary state. Stationary state. So students, a stationary state doesn't mean here that the electron is stationary. It means that till the time it is in the same orbit, it is having the stationary energy. So in the same orbit, it is not losing or gaining any energy. So very clear, it should be very clear to you that the word stationary is not for the electron. Electron is not stationary. The energy associated is fixed. Now the third one. Only those orbits are permitted, the shells are permitted in which the angular momentum, a new word, angular momentum, in which the angular momentum of electron is a whole number multiple of h upon 2 pi. So it is very well to be remembered that only those orbits are possible which have a integral multiple of h upon 2 pi. And what is n here? So the angular momentum is mvr. We know that the linear momentum is m into v. But when we talk about the momentum in the circular region, then it is considered as mvr where m is mass of electron, v is the velocity, and r is the radius of the orbit, about the orbit which we are talking. And n is the integral multiple of h upon 2 pi. So n can be 1, 2 or 3. So it is very well clear that the energy of each of the orbit is going to be a fixed number. It is not any number which can be assigned to it. It is only a fixed number, that is an integral multiple of h upon 2 pi, and h is the Planck's constant that we have studied in the Planck's theory also. So now the third point. The next point is, the energy is emitted or absorbed only when the electron jumps from one energy level to the another. That is, the energy absorbed or emitted is responsible for taking away the electron from one place to another. If it's absorbed the energy, it moves from the lower energy level to the higher energy level. But if it will emit out the energy, it will come back from the higher level to the lower level. It can also be explained in the terms that when energy is supplied to the atom, its electron absorb a fixed quanta of energy, that is a fixed bundle of energy, and it jumps to the higher energy level. As soon as it absorbs the energy, it will jump to the higher energy level. And this energy is supplied to the atom and then to the electron by subjecting it to high electric discharge. How the energy can be provided to that electron in the atom? By using high electric discharge or by using high temperature. The electron absorbs this energy and it will jump from the lower level to the another higher level. So in this case, the word used is, a particular word that we can use for the electron when it jumps to the higher level is the excited state. As soon as it absorbs energy, it is now considered not to be in the ground state, that is the normal state, but now it is considered to be in the excited state. So after absorbing energy, it is going to be in the excited state. Now, moving to the next point, the amount of energy emitted or absorbed. That is, if it is absorbing the energy, it is going from the lower energy level to the higher energy level. If it is emitting out the energy in the form of radiation, it will come from the higher energy level to the lower energy level. So in any of the case, the difference in energy is represented by delta E. Delta represents the change in energy, and the change in energy can be E2 minus E1. Now what is E2 here? E2 is the energy of electron in the higher energy orbital. And what is E1? E1 is the energy of electron in the lower energy orbital. Now if it is absorbing the energy, it will move from the lower energy level to the higher energy level. But if it is emitting the energy, it will come from the higher energy level to the lower energy level. So the next point explains, emission and absorption of energy occurs only. We must always remember that all of the work is done in a particular discrete number. So emission and absorption of energy occurs only in the discrete values, which is always equal to the difference in energy of the two levels, that is delta E. Okay, now it is equal to the difference in energy, that is delta E of the two levels. Thus energy of electron cannot change gradually. It is not going to change gradually or continuously, but it changes abruptly. It changes abruptly as the electron jumps from a lower energy level to the higher energy level, or from the higher energy level to the lower energy level. So it can even be shown as, let us take that it is the nucleus part, and this is, in both the diagrams I am placing the nucleus at the center, the heavy part. So now if the this is an E1 and the higher energy level is represented as E2. So if the energy radiation is provided to E1 part, that is, we are providing the high energy radiation to the E1, a particular frequency of energy radiation is absorbed by the electron. a particular frequency is absorbed by the electron present in the E1 level, then it will move from E1 level to the E2 level. By absorbing the energy, it will move from E1 to E2. So it will get excited and the energy is absorbed. The energy, as we know that energy is directly proportional to frequency, we can say that a particular frequency of radiation is emitted or absorbed. So in the first diagram, the particular frequency is absorbed. Now let us take the example of the other diagram. The E1 is the first level, that is the lower energy level, and E2 is the higher one. Okay, now in this case, the electron is present in E2 and it is coming back to the E1 part. So when it is coming back to the E1 part, that is the E1 orbit, so while coming back also, it will emit out the radiation and of a particular frequency, and this is also represented frequency emitted. So the energy which is emitted in the form of the radiation is corresponding to a particular frequency which is equal to the difference of E2 and E1. So dear student, the difference is always same. Delta E will remain same, that is equal to E2 minus E1. And this difference in frequency depends, this difference in energy depends upon the frequency of the radiation absorbed or frequency of the radiation emitted out. So we can say that the frequency of radiation emitted or absorbed is given by nu is equal to delta E upon H. Nu, the frequency absorbed or emitted, delta E is the change in energy, and H is the Planck's constant. So this is also known as the Bohr frequency formula. This formula is also known as Bohr frequency formula. So these are some very good attempts done by Bohr. Now in the other, now we come to very important formulas as given by Bohr. So these are some important formulas that are going to help us when we will be doing the numerical part. Important formulas. Okay, now the first one, the very important, as we say that the orbits are having a particular energies associated with each of the orbit, whether it is near to the nucleus or it is away from the nucleus. So energies of different stationary orbits, stationary states. So stationary states are actually the orbits which are represented as n is equal to 1, 2, 3, or previously we used to call them as KLMN. So the energies of the different stationary states in case of hydrogen atom is given by, according to Bohr, the energy is given by En is equal to 2 pi square Me4 divided by n square and h square. This is known as the Bohr formula. Bohr formula for energy. Now this formula is very important, but we can simplify it by putting the values of pi. What is m here? M is equal to mass of electron. What is E? E is the charge on electron. What is H? H is equal to Planck's constant. All of you must be knowing the value of Planck's constant, that it is equal to 6.626 into 10 to the power minus 34 joule second. And now when we put all these values, the formula for energy comes out to be minus 21.8 into 10 to the power minus 19 upon n square when it is given in joule per atom. We can also write it as, in most of the question we used to take it as 2.18 into 10 to the power minus 18 upon n square, and represent the orbit number joule per atom. And here remember one thing also, that this particular value, that is 21.8 into 10 to the power minus 19 or 2.18 into 10 to the power minus 18 is known as Rydberg constant for hydrogen atom. Rydberg constant in case of hydrogen atom. But if we convert this value, that is joule per atom, in electrovolt per atom, the formula gets simplified to En is equal to minus 13.6 upon n square. So all of you, as we have done in the Planck's term also, that 1 electrovolt is equal to 1.6022 into 10 to the power minus 19 joule. So electrovolt and joule conversion has to be remembered while doing the numerical parts. It can also be given in kilojoule per mole. But remember, student, that when we are talking about mole, we have to consider the Avogadro value also. So energy can be given in terms of joule per atom. It can be given in terms of electrovolt per atom or in terms of kilojoule per mole. So this theory was given mainly for hydrogen atom. That is, it is for hydrogen atom which is having one electron. But what will happen if we consider the hydrogen-like particles? Hydrogen-like particles include those which are having one electron. For example, lithium positive, lithium 2 positive or helium positive. These are one electronic species. One electronic species, but these are not having the same atomic number. The atomic number is different. So the formula for En is not going to be the same as given for the hydrogen atom. So the formula is going to change a little bit. It is taken as minus 21.8 into 10 to the power minus 19 upon n square into z square joule per atom. So what is Z here? So student, Z is equal to atomic number of the element of which we are talking about. It is equal to atomic number of the element. So if we consider the hydrogen-like species, that is those which are having the one electron, then in that case the formula get multiplied with the Z square. Now coming to some other important formulas of the same topic, that is the formula of radii. As we always talk about that each of the orbit is having a fixed radius. So the radii of the stationary state of hydrogen atom as given by Bohr is Rn is equal to A naught n square. Now you must be revising again and again that n represent the integer value, that is it is equal to 1, 2, 3, 4, the number of the orbit, which we used to call it as KLMN. So now what is the value of A naught here? It is 52.9 picometer. Now when we talk about the radius of the first stationary state, that is the first stationary state when we used to take n is equal to 1, the first stationary state, that is n is equal to 1, then in that case the value of the radii in the first stationary state comes out to be 52.9 picometer, and it is known as the Bohr radius. This is the formula of Bohr radii, and for the first stationary state of Bohr, that is n is equal to 1, the answer is 52.9 picometer and is known as Bohr radius. Now again the same thing come. The formula was given by Bohr is only for the hydrogen. But if we consider the hydrogen-like species, again I am talking about He positive, Li2 positive, which are having the number of electrons same as that of the hydrogen, but their atomic numbers are different. Then what happen in case of radii formula? It is going to be changed little bit, that is A naught n square divided by Z, and what is Z? Z is equal to atomic number of that element. So the formula gets little bit modified when we talk about hydrogen-like species. Now the whole of the Bohr theory was again and again telling us about the integral multiple, the fixed value. So the main concept of the Bohr, the key point of the Bohr theory is quantization of the electric charge, electronic energy, quantization of electronic energy. So what does the word quantization means here? The quantization means that a quantity which cannot change gradually and continuously, it is not going to change gradually or continuously or arbitrary, but it is going to change abruptly and discontinuously to have a certain definite or discrete value. It is having a certain fixed value. As we have talked about that the energy of electron is quantized, angular momentum is quantized, because all of these are changing when we are moving from one orbit to other in the form of their integral values. So the energy of the electron also cannot change continuously, but it can only have the definite value. So and because of this, the energy of electron is said to be quantized in nature, is said to be quantized in nature. So students, till this topic, revise all the postulates of Bohr, go through the various formulas for energy, for radii, the wave number formula that we did in hydrogen spectrum. All of these are very important formulas that are going to help us while we will be doing the numericals of the Bohr theory. So now in the next lecture, we will be doing the application part, the usefulness of the Bohr model, as well as some of the limitation part of the Bohr model also. So till then, revise the Bohr model and its postulates very thoroughly. Thank you.